In this lesson, we will discuss FP growth, another efficient pattern mining method. We will start with a short motivation about why a growth-based method is needed. Then we will go over the details of the FP growth method. Apriori, in essence, is a breadth-first search mining method that starts with a set of frequent K item sets, then expanded to frequent K+1 item set candidates, which involves database scans and pruning to get the true frequent K+1 item sets. So after spending a few years working on Apriori and improving Apriori, researchers started to think on the direction of depth-first search. In other words, instead of starting with a large pool of candidates then prune, it's possible to start with item sets that meet specific criteria and confine the search there. This effort led to the FP growth method. Let's walk through an example to understand how FP growth works. Suppose that we have a database that consists of 5 transactions. Minimum support is 3. The method starts with scanning the database once to find single item frequent patterns. As you can see, F appeared 4 times, A 3 times, C 4 times, and so on. Then it will sort these frequent items based on the frequency in descending order. So we're going to have F, C, A, B, M, P. In the following step, it's going to perform another database scan to find the ordered frequent item sets for each transaction. So for the first transaction, we're going to have FCAMP. Notice that it dropped the G and it dropped the I, it dropped the D because they did not meet the minimum support. Again, for the second transaction, we have FCABM, third transaction FB, and so on. After the method performs the second scan, it's not going to touch the database anymore, and it will use these ordered frequent item sets to create a data structure. For the following steps, the algorithm will incrementally build a data structure called FP tree by inserting item sets in a way that allows a traversal and identifying frequent sets. As you can see, the header table consists of items and their frequencies. Notice how the insertion of an item set starts from its header entry. So this is the FP tree after inserting the first transaction item sets. So first we start with the F, followed by C, followed by A, by M, by P. And notice here we have a counter that maintains the frequency of the item set so far. Now, as we insert more items into the tree, we will start to deal with a number of cases like branching, updating minimum support along the way. Also, you can observe that there's a pointer here that links M from one branch to another branch to the header table. Let's see how to insert the second transaction. I kept the previous step so we can easily compare. After inserting F, the minimum support counter becomes 2, C2, A2, but now we have a B. There is no B in the previous branch, so we're going to create its own branch with 1, followed by M, but M previously appeared, so we're going to link it through a pointer. For the third insertion, FB, we increment the F counter, add the B, link it back to the existing B. For the fourth insertion, CBP, we haven't seen C at the root of the tree, so it's added on its own branch, followed by B and P, which both are linked back to the existing item sets. Finally, for FCA and P, which is similar to the first transaction, so we're going to increment FCA and P along this path. At this point, we are finished from creating the FP tree, which contains all the information that we need to mine those frequent patterns. Next, we are going to create what is called conditional databases. So a conditional database for a specific item set is the database under the condition that this item set exists. In this example, we're creating the conditional database for P. We go and traverse P all the way up to the root. So here we have FCAM, and notice that we write it from the item set that has highest frequency to the lowest frequency, and we record the frequency at the end of the path. So for P, the conditional database consists of two patterns, FCAM with 2 and CB with 1. After that, we identify the conditional databases for each pattern and recursively repeat the process, which is building an FP tree for each conditional database and work our way to identify those frequent patterns. This is the conditional database for M, traversing M bottom up, FCA, and FCAB. Similarly, we find the conditional databases for B, A, and C. Notice we don't need to find the conditional database for F because this is the most frequent item. It already appeared in most transactions. After obtaining conditional databases for item sets, what will happen next is to pick an item set, create FP tree, repeat the process, and we try to mine patterns along the way. In this example, we picked P. P has two patterns in the conditional database. We construct P's one item list, sort by frequency, and we notice here that only C meets the minimum support, which makes things easy. So the frequent pattern at this point is CP with 3 as a frequency. For M's conditional database, we have two patterns, FCA and FCAB. Notice how B is pruned because its frequency is less than the minimum support of 3. When the FP tree is layered as a single prefix path, finding frequent patterns become much easier. Because we already know that the prefix is frequent, then every subset in this prefix is also going to be frequent. We really don't need to do further recursive calls and find conditional databases and construct FP tree. In this visualization, you can see the FP tree for the M's conditional database, AM conditional database, CM, and CAM, but really we don't need to do this work. We can directly go and find all of the possible subsets with their frequencies. Optimization techniques like decomposing the FP tree can improve the runtime performance. For example, if the tree has a prefix, it can be reduced to a single node. Then we can carry out the computations, find the frequent patterns, and then concatenate the prefix part. And this technique lends itself to parallelization. Finally, we have a worked out example to further exercise FP growth. Suppose we have this transactional database with 9 transactions. We applied the FP growth algorithm and we got this FP tree. This table gives the item sets with their conditional databases, conditional FP tree, and the frequent patterns. We are going to follow the I3 paths. I highlighted those in the dark circles. Let's focus our attention on getting the I3 conditional database. One path is through I2, I1, then I3. This is how we got I2, I1 with frequency of 2. Another way is to go to I2, then I3. This is the second pattern, and we can go through I1, then I3. One question one might ask, could you explain how the 7 came here? This means that there are 7 paths started with I2, 4 were followed by I1, 2 were followed by I3, and 1 was followed by I4. Next, we construct the conditional FP tree for the conditional patterns of I3. First, we insert I2, I1, then insert I2. Notice that now the frequency of I2 becomes 4, 2 from the first pattern and another 2 from the second pattern. Then we insert I1 with a frequency of 2 and link back to the previously inserted I1. Next, we recursively find the conditional database for I1, which is going to lead to I2 with 4. Let's take a moment and try to understand how these frequent patterns got generated. For the frequent pattern I2, I3 with a frequency 4, it's clear that the 4 comes from 2 branches. One is direct where it started from I2, and another one, it went to I2, then I1 to I3. For I1, I3 with 4, this comes from the branch I1 with 2, and if you follow the back pointer, it's going to lead you to another pattern where the I1 and I3 happen together with frequency of 2. If any pattern seems to be confusing, you always can take a step back and try to traverse it on the bigger tree. So to get I1, I3 with 4, we followed this branch with 2, and then we followed this branch with 2. Finally, I2, I1, 3 is the most obvious one. It comes from one branch, which is I2, I1, I3. The FP growth method for finding frequent patterns can be summarized as partitioning the data set based on the frequency of the item sets starting from single items, then recursively partitioning the dataset based on the conditional databases of the item sets that continue to be frequent. And as we have seen, there can be multiple stop cases. Sometimes we stop if we encounter a prefix, so we can enumerate the subsets of a frequent item sets. Other times we have to keep on partitioning the database further and further until we no longer are able to partition it, then we can enumerate the frequent item sets. In summary, we discussed the FP growth method, which is a depth-first search approach for finding frequent patterns.